This project involved picking up the car or sensing the car as it passed certain points along the track. These points are called pole positions, and a number of pole positions make up a full lap around the track, and so you want to time the pole positions and that sort of thing. But what's difficult is actually sensing the car driving by. And I initially tried using this module here, which is a motion sensor. I tried to tape it on top of the track or above the track to sense that a car passes. However, the car would pass so quickly that it wouldn't trigger the sensor. And so I quickly decided that this little module wouldn't work. The next thing I tried doing was using a ping module, ultrasonic ping, and this also had some limitations. The car would be picked up, but you had to have a card or some sort of reflective material on the opposite side of the track, and that led to other complications. It was difficult for the car to be picked up because it would actually sense the car in other lanes or even other portions of the track. And so I would get a false positive with this too. Now there is a YouTube video where someone has actually got this to sort of work. It just wasn't a very clean solution. In addition to that, I needed 5 units, and these are all $4.30 each, so it got expensive. The other unit was about $1, and so I wanted to keep it as cheap as possible because I didn't want to spend a whole lot of money on this project. After thinking about it, I realized that the slot cars used magnets, and I'm thinking there must be some sort of magnetic switch, and sure enough, this was the magnetic switch that I wound up using, and it works great. I basically tape it underneath the lane near the metal rail that's mounted in the track, embedded in the track. And as the car goes over this little portion right here, senses the magnet in the car and triggers the magnetic switch, which I trap on a digital input on the Uno. I did have to bend this little diode here, I think it's a diode, down so that it's horizontal and very close to the metal rail. Now I only tested, or I only built it to handle lane 1, but you could do 2 lanes. You would need 2 modules per pole position. You would have to bend this down on both of them, and then this would go on lane 1, and then you'd have another one on the other side that would be lane 2. And that would pick up each car as it goes over. Now, granted, the car you use does have to have a good magnet on it. Some magnets seem to work better than others. But I think if you kind of position this a little bit better underneath the track, you'll pick up that any car that goes by. So that actually worked out quite well. You could even modify the track if you wanted, to bring the magnetic field closer to this diode here, making it work even better. But overall, it worked. No matter how fast the car goes by this sensor, it picks it up and triggers an event, a timing event on the Uno, which sends it to the laptop to be processed by Python. Another thing that's interesting is I had to tie all the modules together to a single pin. I tried to use multiple pins, like pins, I have 5, so I would do 10, 9, 8, 7, 6 pins, digital pins, and read each pin individually. But sometimes the car would go by so fast that a pin would be missed, and so that pole position would not be captured. So what I did is I tied all 5 of these modules to one digital pin. I think it was digital pin 10. And I just monitor digital pin 10 for changing its state from high to low. And so anytime one of these goes low, it pulls that pin low and it's trapped. And so that worked the best for me. Overall, this is a very clean solution. It's a little bit more money than I really wanted to spend at $3.40 each. But overall, it just works great. And now that you can capture the car as it travels around the track, you can use it for all sorts of other different projects. So I'm going to see how I can implement this in other slot car projects. This is the Arduino program that I used for the pole position, generating the gap time. It's a very simple little program. There's not a whole lot necessary to run other than you keep generating gap times, and you want to do that as quickly as possible. I initially had one sensor pin for each of the 5 pole positions, but turned out that did not work. Sometimes the pole positions were missed. So what I did is I used a breadboard and connected all the pole position pins to the breadboard, and then connect the breadboard to one pin, which is pin 9. I called that hall sensor pin 1. That's what I called it. So I'm only polling one pin all the time to see if it goes from high to low, and that made it easy to trap anytime a car went over a magnetic switch. It basically would trap it there, and I would catch it. Now, one thing I did do was, as I was testing, I realized I needed some sort of visual cue, like a light, and so I have pin 13 here, picking up the signal and going bright when the pin is triggered. State 1 here is here we trap that pole position and store it there. In addition to the LED pin, sometimes I had a buzzer go off because I had to look away from the Uno as I was driving the slot car to see it go over the pole, past the pole position. And sometimes it's easier just to hear the pin go off. But I eventually disabled that. That was only for debugging. So you can add a buzzer here too, so that you can kind of hear it as well as see it. And it helps you look away from the PC or the laptop or the track or the Uno, and it makes it easier just to kind of see what's going on. So getting back to the code here, we have a start time. I always collect the start time. And then here's the gap time delta, which is used to store the difference between the start time and the current trigger time. So basically, that's all that needs to be set up. Here's in the void setup portion of the program. I initialize the LED pin for output. I initialize the hall sensor pin for input. I then clean out. I do a flush and flush, which I probably do too much here, but I just want to make sure the serial port doesn't have any garbage in it before we start calculating the pole position times. Next, I do a serial begin 115,200. I want that communication to be as quick as possible to get the information up to Python and to be ready to check the pole again. Then I start the race, or the collecting of time. I do a start time equals mils. I store it in milliseconds, and that's all I do in setup. Here in the void loop, where the program loops, I want this to loop as quickly as possible. I have some code here grayed out. I call it a fake pole position sensor while I was coding the Python software and tkinter information, I needed to have some sort of generated gap time because I couldn't run the car and generate the code and keep everything running. So I did a random gap time between 100 milliseconds and 1500 milliseconds, roughly a tenth of a second to a second and a half. That was plenty of time to kind of generate some numbers. I delay that gap time, so it's actually as if the car has waited and gone from one pole position to the next. So it's an actual physical gap delay. And then I say state 1 is equal to digital read the hall sensor pin. We read this and we see if an event has triggered from high to low. And if state 1 is low, I turn on the LED light so I know that's been triggered. I calculate the gap delta time, which is the time from the start of the race to the pole position, or from one pole position to the next. And then I reset the start time to equal the current time. So then, using the gap time delta, I make sure that it's less than 3 seconds and greater than 0.2 seconds. Sometimes it doesn't collect it or misses it or something, so you get a 0, and that affects the telemetrics in Python. Or if the car comes off the track and you got 5 seconds, you don't want to count that. Or if you got 10 seconds, you don't want to count that pole position because it's invalid. Then I print the gap time delta, which is printed to the monitor, serial monitor, and then the serial monitor must be kept closed or Python won't be able to access the serial port. And this is basically, Python will just read the serial port and take that data out and use it. I then do a delay of a tenth of a second, roughly 100 milliseconds here, just allow this whole printing and everything to complete and that sort of thing. If state 1 is high, then I just turn the LED pin off, turn the LED off, and then I go back and wait to see if it's been triggered. And I test, turn it off, test, turn it off. Basically, that's it. And that just keeps going over and over and over. And that's really the whole program. There isn't much to it. It's very simple. You can have as many pole positions as you want. I used 5. You can have 4. You can have 10. It depends, what your preference is. And it's all connected to one pin, so it doesn't use very many pins. It's a simple little program, and it works very, very well. This is the object tracking program that I run. It's the Python program. There's 2 Python programs. One is the object tracking that gives you the driver name and a little arrow or a little line going down to the car as it goes around the track, and it shows you a live version of the track. I didn't write this program. This was kind of an open source program that was available. I did modify it slightly and remove some code that wasn't necessary, but I feel that it was written quite well, and it uses a very interesting technique to target a color or an object that is colored. And it has a little menu bar that comes up. You saw that, maybe you probably did not see that at the beginning of the video, but it has HSV values, minimum and maximum, hue, saturation, and value, minimum and maximum, and it has a threshold and a mask screen that comes up. Now, I don't use the mask screen. I took that out, but I do use the threshold, and I will show a video of how this kind of works, but I set this all up before I did my video showing the overhead car driving. And like I said, I did not write this. This is actually written quite well. It is a very nice usage of these slider bars. It's quite nice. So I changed this a little bit, and I'll go over it now and explain to you what I did different. You have to load these. You have to import CV2. And this is argument parsing, and I don't like argument parsing. That means you have to run it from the shell console, and I like just to run the program and have it go. So I commented out all the arguments. So this you could probably do this, just take it out as a comment and not have it in here at all. I did leave it in. I'm not sure if it's absolutely necessary, but I don't believe it is. So then you have to import NumPy and then import math, because there's a lot of math and numerical analysis to capture screen video and process it. These two I did add, these two variables I added. A target location is where I want the name of the driver to be stored or to be displayed. So it's up here in the right-hand corner. And video port will change between 1 and 0. Sometimes it's the video on the laptop, sometimes it's the video on the camera, and you just have to try it once or twice to see which one actually becomes active. We come down to this callback. I don't understand what the pass value, I'm not really sure what's going on here. Set up track bars. This is the min and maximum track bars. It allows you to pull, to have a value between 0 and 255 for the HSV, and that changes the color recognition of the video, and I'll show you that. And this just creates the track bar so you can do that. It looks like get track bar values. As you slide the bars left and right, this gets the values and assigns them to, so it looks like a values list or array, and it just appends those values somehow. So I'm not really sure how this works per se. Here's the definition of the main program. Arguments, well, I'm not using arguments, so I commented that out. This used to say arg filter uppercase. Well, I just changed it to HSV because that's the one I want to use. Here's the camera. It's a video capture. Video port is set up here. Set up track bars. Here, I guess it sets up the track bars. And then while this is true, and this is what I put in, I believe, this keeps going over and over and over. I took out the arguments again. We read the camera image. This is some error checking. I took that all out. Frame to threshold. I need this information. It takes the image and converts it from red, green, blue to HSV, hue, saturation, value. And then these are all minimum value, maximum values, which I'm not really sure how those are all set up. The threshold, if it's in a range, I guess it does something here. I don't really know what that does. I'm not sure what the kernel is necessary for. This kernel information, I don't know. I took this information out. I don't need the center dot. This is finding some sort of contours, I guess, of the image. I don't know. Center none. I can't help. I don't know. I didn't change it. So here, this is part of the color processing. I guess you want to make sure there's at least one color found. Somehow there's a contour color here. I don't really understand how this all works. I left it in. I believe it's necessary, but I did not take it out. The radius, since the slot car is so small, I changed the radius of the object that's tracked from 10, that's what it was here, to 5, so that it's a smaller radius. Otherwise, the car sometimes gets lost because it travels so quickly. And here it says it draws a circle and centroid around the frame. Centroid is just a little dot, and a circle around the object. And then update. Well, I removed that a little bit, and I now have the circle around the image. And then I put the text driver 1 up in the corner, and then I added this line that connects a line from the driver's name down to the car. This was some other information that was not necessary, so I took that out. Here's a useful website for generating distance. I was going to do some sort of distance analysis with this, so that's what this was for. This is not necessary for this application, but I will be doing distance calculations in the future. And if you ever need a general equation to do some sort of function, this website is really good. I highly recommend it. You can put in a bunch of data points, and it will generate an equation that you can use to generate those data points again. So the last little bit here is show the frames on the screen. We have CV2 IM show original, which is the colored image, the actual video image, and then the threshold image is used to isolate a color. And the mask, I don't know, I never really used it, so I just commented it out and don't need it. And then this last little bit here allows you to exit out by typing the letter Q or something, or escape. I don't do any of that. I just, because this was originally supposed to be run by arguments. So I think technically this could actually be removed too. This right here. But I left it in. And then here, if it's main, you call main and you just loop around. This is part of the main program. And that is it. It's a very simple little program, and it works very, very well. And I will run it here and show you how it kind of works really quick. Let's go ahead and run this, and I'll show you how this works. So this comes up. Here's the slider bars. Here's the threshold. So let's move the image we have over here, the original. Then we have the threshold over here. And here we have another little track bars. And there's 6 track bars. HSV minimum at 0. That's hue, saturation, and value. And then we have HSV at 255, a maximum value. And that's hue, saturation, and value again. And you slide these bars, and the image here will change. So as I change this, you see it gets darker or wider. It starts to outline the contour of what it sees. But this is getting all kind of random over here. So this is not a good choice. What we want to do is we want to get this image right here of the car, the only white rectangle in the threshold window. So let's start here. I did put foil on top of the car so that it's more reflective with the light and sticks out, and it's easier to target. So you may have to do something like that if you want to have multiple cars. So let's go ahead and try changing this. Let's move this down, and you'll see the white car sticks around, and oh, everything's disappearing. See how that all disappears? Because it now thinks this is the car over here. Well, that's really not the case. We want to start to isolate that, and it is now tagged, but we have all this random noise around here that we don't really want. So let's bring this down a little bit more. More disappears, and then let's bring, oh, the car disappears. That's not going to work. Let's bring this up. Up, car disappears. That's not going to work. Nope, that's not going to work. Now, oh, that's looking better. Now we're getting rid of a lot of stuff. And there we go. So right there, that is the best setting to isolate this. And you'll see it says driver 1 with a line, a yellow circle around it, highlighting the car perfectly. And that's really the best you're going to get. You will always get these little spurious remains of recognized color, because some of this white is, on the top up here, there's a lot of color in this image, even though it doesn't look super colorful. So maybe blue would be good, or a lime green would be good to track here. I had problems tracking different colors. This actually worked as a reflective material the best. And because the car, when it travels, it almost looks like it's going 1,000 miles an hour. You can barely track it. And that's, I think, a reflection on the camera I have. I don't have a very good camera. The frame rate isn't so good, so you get a blurred image. A better camera would allow you to track the car more cleanly, and you could probably get rid of these little spurious things a little bit more and still have it highlight this well. In addition to that, as the car travels quickly, the driver name or driver 1 will highlight the car and follow it longer and more precisely. So the code is very good. I don't know who wrote it, but it's out there. You can see others have used his code too. He did a great job with this little slider bar thing and being able to set up the code here. To capture the color here. So I'm very pleased with it, and I wanted to use it. I made some minor tweaks to give it more of an Indianapolis, an F1 overhead shot showing the active driver. You can do whatever you want. I just wanted to make it a little bit more interesting. And this is a separate program that runs. There's 2 Python programs that run. I set this up and got it working before I started recording the videos, but I wanted to show you how this all works. This is the Python program that I wrote to display the telemetrics of the cars driving around the track as they pass each of the pole positions or magnetic switches from Arduino. It'll read it in from the serial port. It'll go ahead and take that time stamp, which is in milliseconds, and convert it into some useful little statistics, and then generate two little graphs. Now, none of it is really pertinent. None of it is really highly accurate. It just does it. And if you want to take this and make it more accurate, you're encouraged to do so. I just wanted it to do something to give kind of the illusion that when you watch F1, when you're doing your racing, it's kind of like watching F1 racing, where they have the people talking and the telemetrics are on the screen, and they're talking. They're showing all the pertinent information. We watched a show called F1 Survive to Drive, and it talks about the drivers in various F1 teams, racing teams that drive around the world. And it showed all the guys talking on the headphones and all the incredibly interesting stuff. And I thought, boy, that'd be kind of cool to take that and kind of add it to the slot car set that I had. And so this is kind of an attempt to crudely do that. And I hope that you find that you like it and can use it, and by all means take it and make it even fancier and more accurate. You can display it on bigger screens, on multiple screens. I actually thought about having the video of the track that has the driver's name on a big screen, and then having the telemetrics on a smaller screen below it or next to it, say in a garage. And as you're racing your slot cars, all this stuff would be going on during the race. But this is a beginning, and so I wanted to get it out there in case others want to try to use it. So I'm going to try to go through this. I actually used another program that I had used as a template that dealt with temperature and pressure to do some graphing, and a lot of this I wrote myself. It's just some tkinter variables mostly, and some sound files, and that's really all it is. But there's a lot there. It's doing a lot. It's changing colors. The font is different. There's a lot of random numbers being generated. And there's also some real data that's being read from the Arduino Uno up and into the display to be calculated in as it calculates gap time. So let's go ahead and look at this. And then I'll start here with what's imported. The serial is imported so that we can read the communication from the Uno. We import time so that we can use time functions to calculate start time or delay time or gap time, that sort of thing. Tkinter, obviously, this allows us to display a window on a Windows PC. Math, I import that to do some numerical number crunching. Same with NumPy. Matplotlib, that's all part of graphing. Draw now draws moving graph lines. If you want the lines on the graph to move, you're going to need that. Import sys, obviously we need it for executable. This allows us to spawn multiple Python shells and programs. I spawn multiple sound files and have them run on their own, and then I continue processing the program, because I don't want sound files to play and have to wait for the sound file to end before I do any more calculations of timing and that sort of thing. So basically, I kick off a sub-process, which is playing a sound file, and it just plays by itself while this program continues to run doing the number crunching and that sort of thing. I needed random numbers in order to do random things in the program, so I imported random. You need the kill out of the OS in order to kill the sound file, and then signal also is used to kill sound files. So I think that's right. Anyway, you need the signal. You need to import that. So here we have some graph data, 1, 2, 3, 4, plot. You plot I on, tell Matplot you want the interactive mode, and then the count is 0. I'm just declaring some variables. These variables probably should be moved down here. I will probably do that later on, but they're not really commented. But it's part of generating the graphs, the two little graphs. There's part 1 and data 1 and data 3 go together. Data 2 and data 4, I believe, go together in order to plot the graph. I just wanted to plot 2 graphs. You could probably plot, if you had a powerful computer, you could plot quite a few. I could probably do 4 and not really mess up the performance, but after a period of time, it does get slower. So here are some notes. It talks about different functions I needed to find out about as I was writing this, and I saved the website, so you're welcome to click on these and check them out. They're actually quite interesting. Here's just a little note to myself. I use gap in place of pole position. Pole position as a variable is too long, so I changed it to gap. Now, you are going to have to address the COM port and the speed from the Arduino. These always have to match. Sometimes you run the Arduino and you get a different COM port. You're going to have to come back in here and change it. Instead of changing it in the middle of the code, which it takes a while to find, I just have a variable COM port and I change it here. A lot easier. I have 5 sensors, so I have 5 pole positions. These gap times are all set. Minimums are set to a very large number. Maximums are set to a very low number. That way, the first time through, this variable gets reset. I check for, is the min time gap less than the current min time? Well, yeah, anything is going to be. So I set the new min time. And same with maximum. If the max time gap is greater than 0, than the previous time gap, which is 0, which it will be, this value goes away. But this allowed me to initialize a bunch of variables, and I didn't fill up the window, the tkinter window, with tons of telemetrics. I could have done a whole lot more. It just makes the program bigger and bigger. I did some real basic ones. I tried to find some information on TV as I was watching. It gets really technical and complex. So again, I just tried to give the illusion. It's more of an illusion. It's just kind of for fun. So here are all the minimum and maximum average times are all set. Minimum minutes, seconds, milliseconds. This is used to display time as number, colon. So you have minutes, seconds, tenths of seconds, and that's what this all represents. I needed the track length, and actually I've added to my track length, so my track length now is not 65 feet, it's more like 75 feet, so I should change that, but it doesn't matter. So here's some more minimum, maximum current speed. I like to have the gear displayed randomly, so here's a list of an array to hold all the gears. The brake can be on and off. The brake color can be green to be on or red to be off. Here's a brake index. It's the index to the brake and to the brake color array, so they match. And I'll explain that more down below. Here's a fuel, oil, and tire. Is it? These are all lists. Is it low, quarter tank, full? Is the oil low, medium, high, caution, danger? I mean, these are just ridiculous, but it's just to display something. Tire low, normal, high. Okay, so then we have the sound flag. I go through the sound portion of the code twice, because what would happen is it would start at the beginning of the sound, go through all the sounds, and then run the program. And I wanted to go halfway through because I start out with a crowd and some horns and some engines revving, and then there's the countdown. You can hear the beeping countdown. And then once it gets to the last countdown, it gives a different tone. And then the cars start revving up and driving away and whipping around the track. And then you get the people, the radio talk going back and forth. So I wanted to go through twice. And I wanted to stop after the first half when it just gets before the countdown. And then and then once the countdown goes, I start driving the car and everything else takes off. So this also allowed the tkinter window to build and display the data and get set up. Otherwise, it's still trying to bring up the stuff and the sound's all over with, and it just was kind of goofy. So here is some column formatting for putting data windows and titles in the tkinter window. Instead of going down in the code and changing it, I could change it up here easily, and everything lined up really nice. So that was a much cleaner way of doing it. This is the initialization of the Arduino serial port, the port and the speed. I give it 1 second to kind of get set up. These variables are necessary for me to pass variables to labels and do stuff with labels and change label boxes with data in them. So you just set these up and they just kind of sit there. Again, all of this could probably be moved up here. I just didn't do it. So here's the title of the window called Slot Car Telemetrics, and here's the size. And I had a problem with the small little box graphs. For some reason, number 1 figure just never worked. It kept coming up large, and I could never get it to get small. So what I do here is I plot the number 1 figure. So you number them, number 1, number 2, number 3. You'll see mine say 2 and 3. I go ahead and plot figure number 1, and then later on I destroy it. I kill it right away. I don't do anything with it. And then I plot figure number 2 and number 3, and they come up perfect size. I could never figure out how to get that to work. So I just kind of jerry-rigged it by adding 1 and then deleting 1. Here we set up the text boxes for tkinter, and I went over this in another video, but I'll go over it quickly here. Here's a label laps. The text is the number of laps, the column it's in, the row it's in. Text box is the height, the size, the font, and the font size. And then text box number 1, where you place it, column 1, row 3, plus some box offset. And so these I kind of just hard-coded. The gap time, the race time, fastest lap time. These are all just kind of boxes that I generated. There's slowest lap time, average lap time, current pole position. Let's see, I have fastest pole position time that's between... I had a reverse text from slowest to fastest. That I realized I had those reversed. Here's slowest pole position time, and then average. Now, here I then in another row I have fastest lap. I want to keep track of that. Slowest lap. I generate a bogus speed. It's just kind of a random number that I display to kind of give a simulation of a speed and of the car. It's like I said, it's just for display purposes. The maximum speed, the minimum speed is based on this speed. It's just stored value. Track temp, air temp, and wind speed are all set. There's no actual calculation of that at all. I guess if you wanted, you could have little sensors that would send up that data, but that seems like a little bit much. Same with humidity. Of course, there's no gears in slot cars, so I generally just have a random gear that comes up. The brake, whether the brake is on or off, there's a green or red box saying on or off displayed underneath the brake. The fuel, oil, and tire information is, again, random also. It's nothing, it's out of those lists, right? Fuel, quarter tank full, oil, caution, tires, low. I mean, it's all bogus, but it's just something to display. You could come back and add data in there if you wanted. With my little laptop, I can only do so much, so that was the best I could do. So now, once I run the program, I print a start here so that I know that everything's been initialized and we're actually running the program. And here I did some testing with some of the sound files. I wasn't sure if it should go here or somewhere else, and it didn't work very well here, so I have these commented out. But you could theoretically have some audio here of crowds clapping and horns going off and stuff like that. These are some functions I created. Timestamp. I needed that information. I needed the actual timestamp, and then I format the time. I converted it into minutes, seconds, and then fractions of a second. and then I return that string, which is displayed in the text box. Here's make figure, which is another function that I've used before to generate graphs. See here I do plot close figure 1, and then I do plot figure number 2, figure size 2, as small as possible, and then I build figure 3. I call it min versus max. That was just made up, and then the Y label time, that's just made up. We do a grid. And then here we do the same thing in figure number 3. I call it time, and there's time. So I don't really know what these are doing. They're really just, like I said, just showing numbers or showing graphs going across. I want to show that you can run all this stuff and even have graphing going at the same time, and it still works. So I didn't really go into graphing real data here, but I could have. Now I set up some variables here for the window. You can't show fastest lap and slowest lap and average lap if you haven't run a lap yet. So I fill it with dashes to show that that data is not available yet. And then here, start time equals timestamp, and that's up here. I get the timestamp, and that's important because that's used to calculate gap time and all sorts of other times. Now we get into the actual program, while 1, which means do this forever. We have lap telemetrics. We have a count total of laps, gap total number of gaps, total time, gap time. Here's where I generate a random break, 0 or 1 for on or off. Text box 1. This is the font, and this is part of the break. It shows the different colors, and then this is where I place that information. So that's basically the start of the lap telemetrics. Now we have more. We have minimum gap time, maximum gap time, and then we calculate a speed, and I kind of take the length of the track, and I do some fudging with numbers, and I get this pseudo speed that kind of falls in a range that the car could actually be between, say, 30 and 200 miles an hour. I definitely want to make sure that speed is is less than 300. I don't want it to be over. I don't want it to be 500, and I want the speed to be greater than the max speed, which is like 32 or 35 miles an hour. And so, max speed is the current max speed, and so if it's greater, then I reset the max speed. Now, if the speed has to be less than 300, the speed also has to be greater than 30. No one's doing 20 miles an hour on the track. And if the speed is also less than the minimum speed, reset the minimum speed. So this sets the maximum speed, this sets the minimum, and sets the guideline that the maximum can't be over 300 and the minimum can't be below 30. The gap telemetrics. Here we set up the number of pole positions. We set the gap count to 1. Basically, total number of laps is minimum, maximum, same as the speed. And then we get an average, and that's what we use. Total gap is equal. We keep a count of the total gap time, total lap. We keep a total of that. Minimum time gap is equal to max time. We then reset that. The max time gap is 0. Lap counter equals lap counter plus 1. So we just increment the number of laps. And here's the average gap. We set this information. We format it in the time format so that the average gap time is in minutes, seconds, and then fractions of a second. And we do that for fastest gap, slowest gap, fastest lap number. We just convert the fastest lap number to a string, and then the slowest lap to a string, and we tabulate this information and store it and then display it. Here are some more of these same variables. Lap variable, here's the lap counter, it's converted to a string. The gap variable is, we format the gap time. Race variable, format the time. We use timestamp minus start time. That's how long the race has been running. Interval gap time. We take the gap and we convert it to a string. Again, we format some time here for minimum time gap and maximum time gap, and then average time gap. We want it in minutes, seconds, tenths of seconds. Here's the speed variable. We need to use that. And that's part of the variables up above, up here, where we declared them. Speed variable all in here, that sort of thing. Here it is right here. It's a string variable. You have to link those two in order to print to that box. So that's where we do this. We set all those variables to a string, and we format them depending on what we want to display. Here we want to display the speed, the max speed, the min speed. In order to pass those variables to these text boxes, you have to have a variable like that. So that's just how it works with tkinter. Let's see, we go back down here, and actually, I'm sorry, let me be more clear. This sets up the box and displays the box, but if you want to put the data in, this is where the data, clear the text boxes, and this is where the data gets stored. You'll see that lap variable get is this information up here, lap variable set from this. So this data here gets placed here in text box number 1. And then we just put in all the variables that we have, and I guess I have about 24 of them. And what you need to do is you delete the box, and then you insert the new data, because this data changes all the time. And so you always want to clear it out, insert the new data, and you want to do that every time you display a box. And then you update it, and it displays the new data. So now we want to plot the actual data in the little charts. And so here I set up the data to be set in a data array. I want to plot the gap time, the count gap, the minimum time gap, and the max time gap. And this is, again, this can be any variables. I just picked these. And here's variable 1, variable 2. That means data array 0 and data array 1. We take that and we append it to graph variable 1 and graph variable 2. And then we do the same with data array 2 and 3. So this data array always starts at 0. And so we're going to plot these two, and we're going to plot these two in the graph, X and Y plots. We append all that, so we build up our graph array. And then we draw now, which draws make figure 1, which I think is up here. Make figure 1. It takes that data, it passes the array, and this uses the array to generate the graph. Now I say the count, now getting down to here, if we have more than 50 points in our little graph, I don't want to display off the side and we miss it. So basically, if the count is greater than 50, we start popping off the lowest data. So we always have 50 data plots displayed. Otherwise, it gets to be just a blurry mess, or it becomes just a flat line. Now I have some other notes here that help me with the sound. This probably could be moved up above. These are great websites to get information, and so I wanted to keep note of that with this file. So here we start our sound file. And I say sound flag equals sound flag plus 1. And since sound flag is initially set to 0, it's going to be 1 the first time. If sound flag is 1, we play these sounds. We play crowd applause. And then you sleep for 1 second. But when I was recording the video, I removed the delay because it took too long for it to start up. So if you want to use it just in your house or in your garage or whatever, put this back in and keep it there, because it gives it a little bit more realism. And so basically I have a crowd applause 1, 2, 3, a bunch of crowd applauding, cars starting. Well, sound flag 2, if sound flag 2, well, it's not. So the first time it's going to jump over all this code and move on and continue on with the program. The second time it's going to come through, and sound flag, since sound flag is equal to sound flag plus 1, on the second case it'll be 2, and it won't play this, it'll play this. which is exactly what you want. And so start this countdown. It starts to do a beeping bump, 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 and the very last one is like a horn, and then all the cars start driving away and start passing. You can hear them passing. And I gave it a little bit of sleep time so that you could kind of hear it and kind of experience it. But like when I said earlier, since it took so long to set it up, I took it out. Then I kill some of those car passing. It just gets to be too much. And I start up some new car driving. You can hear people talking, and then some team radio talk. And I wait a little bit, and I kill a few more of the car passing because it gets to be a little bit too much. I do an air wrench noise here, and I kill that. And I get rid of some more of the car passing and driving, and I leave a few open. I don't wind up killing all the, all the radio team talk. I leave that mostly running, so you can hear the people talking and a few of the car driving, and that's all I leave running in the background. And what you'll have to do is you have to open up your task manager in your Windows and go down, scroll down, and kill those jobs, or end those jobs in your task manager, because they won't stop. They'll keep running even though you shut down all your Python programs. You could do a key sequence that may kill it, but I didn't do all that. I just go in and kill it. So anyway, here it plays the sounds. And then we get to the meat of it. This is wait for the serial port for data. While Arduino is equal to 0, wait. And you just continue to sit here and go through and update this information, which is really just the race time. Race var is the race time, and it just keeps adding the race time over and over and over and over and over. It's timestamp minus start time, and it's set to the format function that I described above, which is minutes, seconds, tenths of seconds. And it just keeps displaying that over and over and over until some real data comes in. And once data starts to come in, then it starts processing the other code, up here and doing some of the number crunching, that sort of thing. Once the while is done, we say the gap time is equal to the Arduino serial read line. We read, there's some data here. It comes down to here. The gap is equal to the serial monitor port, or the serial port, divided by 1,000, because I want the timestamp to be in a fraction. So instead of being 1,200 milliseconds, I want it to be 1.2 milliseconds. And then the root main just is the end of the program, and the whole thing cycles over and over and over and updates the screen. And that's the whole program. It does a lot. It could do a whole lot more. It could be much more accurate or much more precise. I wasn't really looking to be precise. I was just looking to be able to do something. I will make it more precise in the future and have it more features, but I'm going to need a more powerful laptop to do that. And that's basically the whole program.
So this is the screen of the Telemetrics. It's really basic. A lot of the data is not accurate. A lot of it is just representational. The track temp and this sort of stuff stays stationary. It's entered once and it stays. The gears are random. The fuel and oil and tire pressure are random. The brake is random. The time of the race is correct. The gap time is correct. The number of laps that are counted are correct. The fastest, slowest is correct. The speed is just a random number that's kind of generated to represent the speed on the track. It's just pseudo-generated. So we trap the maximum speed, minimum speed. But again, those are all kind of faux. The fastest, lap time, slowest, and average are all correct as far as calculations. The pole position is correct. It's triggered every time the car goes by one of the magnetic sensors. The fastest, slowest, and average pole positions are all calculated correct. So some of the data here is accurate. but some of it is just typed in once and kind of just set there to show that you could have other information come in and actually input real data if you wanted. But again, I'm just trying to do all the telemetrics. I'm just trying to show how you can trap some of it and kind of simulate an F1 racing. I do two figures here down here, min versus max, and then one that's called time. Again, these charts are just random information gathered up here and then plotted. And you could probably have 2, 3, maybe even 4 charts going or more if you have a decent graphics processor and a decent camera and all that. I don't. The data down here, the charts don't actually use the camera, but the camera usurps some of the power or some of the processing power and slows down the whole process. So again, I'm not really using a high powerful computer here to show you this simulation, but if you had a better processor and PC, you could definitely increase the performance of this software.
I hope you enjoy these videos and use them, and I hope they help you with your projects. Please share them and download the source code and use it freely. I would really appreciate it if you would subscribe to my channel, my YouTube channel, and that way in the future I'll have more projects that you can watch and use, and hopefully that will help you. Thanks.